soil against the face. So these hard rock, these good modern HP meat machines are designed to actually operate with a full face of loose rock against them. We can zero down to 0 to 1 or 2 RPM and just rotate with real high torque and keep advancing with a full face of loose rock in front of it. And at the same time, then we've got to contain that rock, that loose rock, with good rock support. And I'm a big advocate of putting up channels with long rock bolts and screening and using a magnetic system, and we can still progress in the conditions as we show here in this slide. And the old one of squeezing and bursting, which was the question asked, we converted a machine, and are still converting this machine for a tough condition in the Andes where we got a lot of squeezing and bursting. And really the only approach to dealing with that, in our view, is to do 270 degrees, have the machine equipped so that you can do 360 degree rock bolting, put in good long rock bolts, and then actually put in channel and use these, which are on the market now, use these yielding rock bolts. And what that does for you, of course, is if you use these yielding rock bolts, if we put in for example, if we're doing a 5-meter tunnel and we put in one of these 7 or 8 meter long yielding rock bolts, then we think that we can take as much as up to a half a meter expansion or squeeze. And okay, the channel will distort a little, the rock bolts will stretch, but at one point, sooner or later, that ground's going to come into equilibrium and you're going to be all right. I think these expandable, stretchable, or yieldable rock bolts are a great invention, and I think we're going to start to use them. We're just starting on a couple of projects, but I think we're going to see them enter in a big way into our tough conditions. And I can see how we can rotate the cutter head even with a full loose rock all the way around it. And if we get this system in behind the cutter head right as soon as we can, I think we can just bore through the rock conditions and put up these yielding supports and make good progress. You know, this is titled Open at Your Own Risk, probe drilling, imaging, and grouting. Open at your own risk is when we bore into a fault zone or some very difficult ground and something bad is about to happen to you. So that's why we promote a lot probe drilling, continuous probe drilling. And also this imaging, it's getting a little better. It's still not as good as we would have liked. The imaging is trying to forecast ahead of you by some, not rock radar, but usually through some other instrumentation, what's in front of you. And there's a couple of companies doing it. One in Switzerland is doing quite well. And that's some advantage, but it still isn't up to as good as probe drilling in our opinion. You should be probe drilling to look to see what's in front of you. And if you don't do it, if you don't probe drill, you don't find what's in front of you, of course, this is what happens. This is obviously back to my copper band in India. There's a double shield. Everybody's thinking, oh, no problem, we're just going to bore through here, and if there's any loose ground or problems, segments will take care of it. But, of course, the segments don't take care of it, and here there's a classic case of that. And again here, had probe drilling been done right, and had grouting done in front of the machine, we wouldn't have had a tunnel here full of muck. So stopping the project for years actually. So it's very important to probe drill, and it's very important that you have the capability to do 360-degree probe drilling 20 or 30 meters ahead of the machine. And most of these machines we can equip with such probe drilling arrangements after about 5 meters. It's very difficult under 5 meters to do what we're doing, what we're showing here. And yeah, this is just good practice. when something, if faults are expected, a 360-degree probe drilling should just be built into your equipment. And as I said, I run this thing about 40 minutes. I'm very interested to hear some feedback from the audience and try to answer questions. We'd all like to have a tunnel looking like this when we're finished, with no problems and heading down the nice curves. So I'm opening up this seminar for any questions, because a lot of you have a lot of experience, and the only way we learn is through experience. So please proceed with some questions.
I will be reading these questions to Locke, and he'll be answering them. One question that came in is, what challenges will you face in the Pahang Selangor, which I may be saying that project name wrong, project, considering the high overburden, possible risk of water inflow, and relatively small diameter? Maybe you could give a little bit of insight, Locke, about this, or background information about this project. It is in Malaysia and coming up later this year.
Yeah, that tunnel is 43 kilometers long, or 45, or might even be longer. We're supplying three 5.2 meter diameter machines on that project. It's hard rock, it's granite, and we'll start pouring in a couple of months. We're just testing on the machines now. Yeah, that is a long, difficult job, but fortunately, I've studied the geology on that project, and fortunately, I don't think we expect too much differential in pressure. It's a granitic mass through most of it, and when you have that situation, you don't. It's not as bad as where you've got upheaval in the Andes, or the Andes, or the Himalayas mountains. They're the tough ones, where you got huge upheavals and high rock stress. Malaysia, I don't think it's going to be too difficult a job. We're going to have to probe drill all the way. We can have water problems. We're set up to probe drill, and it's real hard rock. We've got 19-inch cutters backloaded on that one. So I'm pretty confident that we'll see fairly good results on this particular project. Next question.
There's another one that is project specific. In your opinion, what should have been done to prevent the rupture of the segments on the Tapavan project that you were talking about earlier? Grouting, and to what criteria?
Yeah, what should have happened there? They should have been running a continuous probe drilling and picked up the fault. It should have been grouted. And the other thing that apparently wasn't done was they should have monitored muck output, volume of muck coming out on the conveyor or out on the muck cars, to advance rate. Obviously, they got big cathedraling over the tunnel, over the machine, and big cathedraling can only occur when you're taking out more muck than you're advancing. So several errors were made. They were not monitoring the advance rate to the amount of muck removed, and they certainly weren't. If they were probe drilling, then they're blindly probe drilling and not doing anything about it. If you got high water and big water pressure, double shield is not a sealed EPD machine. There's no sealing system between the lining. The double shields aren't sealed. Theoretically, we could build one, or our competitors could build one, but neither of us have. So the segments, if you have water and a double shield, you gotta rub it off, or you gotta live with it to get the segments, and that's an operational decision. So to answer the question again, probe drilling should have been done. The machine should have been equipped up front so that you had good facilities to do 360-degree grouting. Hard to do on a standard double shield, but designs are available where you can do good grouting up front. And I don't argue the case that segments weren't the proper thing there. The segments could have been the proper thing for the tunnel. I know we looked at that project, and I was okay with segments. I wasn't okay to have a classic standard double shield where you can't do good probing and grouting up front.
Another question, what do you think about pre-injection?
Well, the the specialists that are on pre-injection, the people that really know that, they claim that you can just turn just about any type of ground into solid form that you could actually tunnel through. So with all the current available grouts and all the current good gels and grouting practices that we have today, you can, if you can at least put a 1 meter probe pattern in front, hole pattern in front of you, you can set that up so you can bore through it. It may be timely, it costs a lot of time, but you can set it up so you can bore through just about any ground, even if it's merely running clay, you can make that solid.
Another question kind of along these lines. Are you continually surprised by the number of contractors that just refuse or fail to probe drill?
It's always a surprise, but look, I understand human nature. The main thing is to try to make meters, and you relax your guard. If the ground's good and you're running along, it takes time, and it's not fun to probe drill a lot of cases. So when the ground's good, or where you go, you just don't probe drill. Then one fine day you find that you should have. So it's a discipline thing in tunneling. I understand why people don't probe drill. It's noisy, it's cumbersome, it's problematic. And so, surprise, no. Poor discipline in tunneling, yes.
All right. A clarification question about earlier in the presentation. I don't know if you want to go back to this slide, but I think the attendee was referencing slide 43 with the severe condition. And his question was, what was the TBM checking against when the machine was used in this manner? I don't think we maybe described fully what type of machine is displayed there.
Yeah, that's right. Actually, that's an open gripper machine, and it's thrusting off the grippers as an open machine. And I guess the question is, hey, what if the collapse is on the wall side, and how do you grip in then? The answer to that is actually in very severe conditions where the wall has collapsed. First of all, you try to keep the circular by putting up steel ribs and using a McNally type system. You try to keep the wall in place. And the grippers on these machines are designed to take a certain amount of nonconformity of wall and still grip. And if it gets severe, then you have to reconstruct the wall with shotcrete, which is quite often done. You just go in and reform the wall into a circular with shotcrete if the fallout has occurred. You recreate it with shotcrete and then grip on it. And that's how you proceed in those really tough and difficult situations where you actually lost the wall. Yeah, that's a good question, and certainly that's at that point the TBM crew they become a bit like artists or artisans, not machine operators, and that is quite often required in severe tunneling. Next question.
Another question. Yielding support consisting of shotcrete, rock bolts, mesh, and high deformable concrete has been successfully applied in conventional tunneling. Do you think this technology could also be applied in combination with TBM?
Yes, most certainly. I think it's my belief and my hope that we can utilize that. Certainly everything we're trying to do is nothing more than duplicating what is done with NATM so what we're trying to do is at least move through those bad ground sections, putting up that type of lining as fast as you can do with NATM. And if we achieve that in those sections, I think we've done a great step forward, and I think it's doable. Because, of course, the advantage of tunnel boring, boring with a machine, is that when you're in good ground, absolutely no drill and blast operation or NATM can even get half the rate. And so the goal for us as TBM designers should be and that's why our company is at least focusing on this a lot, is to try to be able to duplicate the advance rates and the support techniques that are that are available and used in NATM.